Matting is the process of separating foreground objects from imagery and is commonly used in special effects for films. In this example, we remove the actor from the scene. An alpha matte is computed, the foreground is separated, and the foreground is composited onto a new background. The most common approach is blue screen matting, where the actor is filmed in front of a blue screen. Though effective, it is expensive and requires studio setup. Manual approaches to matting include rotoscoping, where the artist directly draws the mattes. Though highly time-consuming, it can be effective for hard edges. More complicated regions, such as hair, are much more difficult. Recently, new methods have been proposed for still image matting, which require no blue screen and can handle complicated regions. These require an input hint image, also called a trimap, which partitions the image into foreground, background, and unknown areas that may contain fractional alphas. An alpha estimate is then computed for the unknown area, the one shown here by a Bayesian approach. Finally, a composite image can be calculated. In this paper, we introduce video matting, which extends still image matting techniques to moving images, such as this sequence. Our system is composed of three main components. Trimap interpolation computes a trimap for every frame in the sequence. Bayesian matting computes an alpha estimate. Finally, when possible, we reconstruct a background to improve our results. We first show the process of trimap interpolation. The first step is to draw trimaps for keyframes. In this case, 11 keyframes are used for a 90-frame sequence. Using optical flow and techniques described in the paper, we interpolate the rest of the trimaps. These trimaps are used to compute an initial alpha estimate. We show a composite over a uniform background. The results are good, but there are some artifacts. We identify problem areas in the mattes and clean them by hand. Additional keyframe trimaps are automatically created for any hand-edited frames. In this case, we add a total of 2 frames, each in different parts of the sequence. The edit will be propagated to neighboring frames automatically during the repeat trimap interpolation. A final set of mattes is computed. Notice the fractional alpha in the hair region. The foreground is shown here composited over a novel background. Here is another sequence with large areas of hair that would be difficult for manual matte painting. Here is the resulting composites using our technique. It needs improvement. We improve results by reconstructing the background. First, a rough rectangular garbage mat is used to remove the foreground. We then reconstruct the background by filling in pixels from neighboring frames. Here is the result. We use this background for both trimap refinement and better alpha estimation. The choice of the Bayesian still image matting algorithm is important. Notice the temporal artifacts in the result using the Rizone-Tomasi algorithm. Here is the composite sequence. Notice the improved fractional alphas. For other test sequences, we show a possible usage of video matting for film production to edit the background. It would not be possible with blue screen techniques. In this sequence, we added signs to the background. This is a faster moving sequence. We add a flower pot to the table. We also give the dinosaur a companion. Using Bayesian still image matting, we've extracted the dinosaur from the background and added a reflected copy to the scene. These scenes demonstrate success for fast-moving, hard edges. Finally, video matting also performs well on another difficult type of effect, smoke. In this original sequence, we've decided to add a few instructive signs. Notice the fractional alphas of the smoke plumes. Our results demonstrate that a combination of semi-automatic techniques can be used to extract accurate mattes from complex video sequences.